Hello and welcome to the first video on Section 2.8, Related Rates. In this section, we will explore an application of implicit differentiation. Equations are used to describe a relationship between variables and constants. From Pythagoras' theorem, which relates the sides of a right triangle, to the volume of a cylinder, which relates volume to the measurement of height and radius, to Einstein's mass-energy equation. Physical laws are expressed by equations which relate important concepts. These equations describe a relation in a static time frame. Take Pythagoras' theorem. If the opposite and adjacent sides of a right triangle were of length 1 today and length 2 tomorrow, all that we know from Pythagoras' theorem is that the hypotenuse is the square root of 2 today and the square root of 8 tomorrow. Through implicit differentiation, we may determine the rate at which these variables change. Similar to our experience with position and velocity, differentiating equations which relate variables in an instant in time will introduce rates of change. Our goal is to relate these rates of change. Let's take the example of a drawbridge. Suppose a drawbridge of length 10 meters is lowering from an upright position, and the end of the drawbridge has a very long chain dangling from it. As the drawbridge lowers, the acute angle theta will be shrinking, and the length of the chain off the ground h will be getting smaller. Also, as the drawbridge lowers, the chain will lower to the ground with a measurable speed. Suppose that the speed of the chain is measured at 1 meter per second when exactly 5 meters the chain is off the ground. We record this as dh over dt, the change in the length of the chain with respect to time, and note that it is -1 as the length is getting smaller. Can we use this information to determine how fast the angle theta is changing at that specific instant? In other words, can we determine d theta over dt, the rate of change for theta with respect to time? dh over dt and d theta over dt are rates, they're derivatives. Our goal is to relate these rates. When solving for related rates, you generally want to follow 4 steps, though the first 3 steps are actually questions to ask yourself as you begin to understand a system. Think about our drawbridge problem. We begin by asking what is variable and what is constant, and we've only talked about 3 concepts: the length of the drawbridge, the angle theta, and the length of the chain h. Now, h and theta are variable, while the length of the drawbridge is constant at 10 meters. Our second question, which rates are known and which rates need to be found? When h is equal to 5 meters, the rate dh over dt is -1 meters per second. So we have one rate that's known, dh over dt, and we have a second rate that needs to be found, d theta dt, the rate of change of theta with respect to time. The third question, what equation relates the variables, can be answered by considering the geometry of the situation. The drawbridge and chain outline a right triangle with hypotenuse length 10, angle theta, and opposite length h. Therefore, a good equation is sine theta equals h over 10. We've answered our first 3 questions. Now we will use implicit differentiation on our equation to relate the rates. Consider for a moment which variable you are differentiating with respect to. As our rates are over dt, we will proceed with differentiating with respect to t. Keep in mind, when differentiating theta or h, you are left with d theta dt and dh dt. We now have an equation which relates our rates. We're searching for d theta dt when h is equal to 5 and dh dt is equal to -1. We can use our original relation to determine theta. When h equals 5, we have sine theta is equal to 1/2. The question is, what is theta? As the drawbridge lowers through a quarter circle, we can assume that theta is in the first quadrant. Therefore, theta must be pi over 6 when h is 5. Substituting into our related rate, h, dh dt, and theta, recall from the unit circle that cosine pi 6 is square root of 3 over 2. And we calculate that d theta dt is -1 over 5 times the square root of 3. And notice that this has units, it's radians per second. By differentiating an equation relating variables, we can relate the rates of change for those variables. In our example, as the bridge is lowering, the speed in which the chain hits the ground is connected to the speed in which the angle of the drawbridge approaches 0. Let's take another example. Suppose a particle is moving along an ellipse. The equation relates the horizontal coordinate x with the vertical coordinate y. Therefore, we can use it to relate the horizontal rate of change with the vertical rate of change. Let's answer our questions. 1. We have two variables, x and y. 2. We know that when x equals 3 and y equals 3, that dx dt, the horizontal rate of change, is 2. We need to determine dy dt, the vertical rate of change. Notice on our graph, at the point 3, 3, we are told that the particle is moving horizontal at 2 units per second. That means that we're moving to the right. Seeing how the ellipse turns, we should anticipate that the vertical rate of change is negative. 3 and 4 together, we were given our equation in the problem, and our rates are with respect to time t, so we will differentiate with respect to t. Don't forget that xy is a product. You need the product rule when you implicitly differentiate x times y. Take a second to simplify the expression on the left. Now substitute the known values. X is 3, y is 3, and dx dt is 2. Solving the equation gives dy dt, the vertical rate of change, is negative 2 units per second. Notice this is negative like we expected. We'll end with a final example. Like our drawbridge problem, a diagram is often helpful when answering questions 1 through 3. Take a few minutes to challenge yourself. Pause the video and solve the problem. Let's begin with a diagram. We begin with a man who's walking along a straight path. A spotlight on the ground 15 meters from the path is kept focused on the man. As the man walks to the right, the spotlight will be rotating with him. We solve this problem by asking our 3 questions. 1. We have a constant 15-meter distance between the spotlight and the path. The variables we will assign will be theta, the spotlight rotation, and w, how far the man has walked down the path. 2. We are given that when w is 4 meters, dw dt, the speed the man is walking, is 4 meters per second. Our goal is to find d theta dt at that instant. 3. We have diagrammed a right triangle with angle theta, opposite length w, and adjacent length 15. And the equation relating these variables is tangent theta equals w over 15, our opposite over adjacent. 4. We differentiate with respect to t. We're searching for d theta dt, so we'll send secant squared theta to the other side. And because 1 over secant is cosine, we find that d theta dt is cosine squared theta over 15 times dw dt. Now we run into an issue because we know w equals 4, dw dt is 4, but we don't know theta. We can use our original equation, substituting 4 in for w, to find that tangent of theta is equal to 4 over 15. And with a bit of trigonometry, that is equivalent to saying that cosine theta is 15 over the square root of 4 squared plus 15 squared. Substituting for cosine theta in dw dt, we obtain d theta dt as approximately 0.25 radians per second. Be sure to familiarize yourself with the steps to solve a related rate problem. Our second video on 2.8 will deal specifically with three-dimensional geometry.